Thanks everyone for being here. My name is Hao, and I work for the Apache MXNet science team at Amazon AI, which is part of AWS. So today I'm going to introduce a new package that we're developing. We are under development to accelerate your large-scale machine learning applications. It's called NP on MXNet. So let's first talk about what is MXNet. And so it is an open source deep learning framework under Apache. And our new package is a new NumPy compatible interface that will allow you to retain your familiar NumPy functions APIs. Meanwhile, also allowing you leveraging the parallelism of modern computer hardware. And also it is providing you with extra deep learning features. So what exactly does that bring? So one thing is that we are definitely maintaining the interoperability with official NumPy. And meanwhile, we are also providing parallel acceleration for all the existing NumPy operators. And we have provided extra operators and functions for your deep learning related workloads. And another thing we're introducing is the automatic differentiation functionality. So let's just take a look at the actual CSM actually running in the Jupyter notebook. So the first feature I'm going to talk about is the interoperability with official NumPy. So that means you can use it with any existing functions implemented with official NumPy. Let's take a look at this example, which is just a moment. Yes. So here we are importing the NumPy and the NumPy extension module from MXNet. And we are also importing the original NumPy as the official NumPy. And then we're creating two arrays here that is our NumPy in the array. So if you print the type of them out, you can see this is of the MXNet NumPy in the array. So now we are trying to add them up using an official NumPy's function. And you can see that works. So it will give you back, it will just dispatch to our implementation of the plus function, and it will give you a result, this C. And this type of C is still MXNet NumPy in the array. So you can also, so this is a ufunc, you can also call another function sum to sum maybe along the zeros axis. And then we get another tensor that is C-sum, which is also still a MXNet NumPy in the array. So this means if you already have some helper functions of your own defined in official NumPy, as long as if you feed a MXNet NumPy in the array to it, it will just function as normal, as before. So the next feature I'm going to talk about is that we provide a parallel acceleration for the existing operators. So if you take a look at this example, so this is a very simple piece of code. We're trying to create two very large tensors, matrices, and we're trying to perform a dot product on them, right? So this is pretty simple. So if we just do it with the original official NumPy, it just look like this. So we measure the time. We can see this. So we do the operation as normal, but we also measure the time it takes for it to finish. So we can see this consumes about 0.072 seconds. And so this is actually done on a pretty good server machine with 32 CPUs. So if you're already spending that kind of money, you would want something more, right? So if we just switch to our library, by just re-importing from MXNet. And we are still just calling it in the same way. And we measure the time, we can see we get a 0.06 seconds on CPU. So that's about 1.2, 1.3 times speed up with just a change of the library on exactly the same machine with exactly the same hardware. So now we can take it to another level that we want to run on GPUs. So to run on GPU, it's really simple. So if you just use the as in context, you can just put it on any GPU. So you can index your GPU, like if you have multiple GPUs, you can, so they have indices of 0 to I-1. And then you can just put it on any GPU. So as long as you put your operands on the GPU, then you just call the function as usual, and the operation will be automatically dispatched to GPU computation. So here we can see this only costs the exactly same operation costs us 0.0034 seconds on the GPU. So this is about a 30 to 40 times speed up just by moving your data, and it's just like a two-line change. So we can see how powerful the modern hardware is, and definitely we want to leverage the parallelism of them. So another feature I'm introducing.
Just a quick question. Do you have a comparison on the GPU without MXNet, just a regular numpy calculation on GPU versus?
So numpy currently does not work on GPU naturally, but we can definitely compare with CuPy if you want the data on it. But I actually don't have that data in hand. Yes. So yeah, the next feature I'm going to talk about is the MPX deep learning operators. So in deep learning, there's a lot of new operators created to serve different purposes. So for example, let's take a look at this convolution operator, which is applied on maybe an image, or you can also apply on like 1D data like audio signals, and also maybe 3D data like video snippets. So let's take a look at how this works. So in convolution, we have a kernel, or we also call maybe filter, that is sliding on the input image. So for every position it arrives, it's the weights within the filter is multiplied element-wise with the input data, and then summed up to generate a new value. So we can see this one is multiplied with this one, and this one is multiplied with this 0, so it's a 0. So this one is multiplied with this guy, and this is multiplied with this guy. So in the end, the sum is 4. So this is usually used as a feature extraction method in deep learning that is automatically learning some patterns or those kind of things. So another operator I want to talk about is like pooling. So it's like a convolution, but without the kernel. You directly extract, so you have a window sliding on the input image, and then you directly derive some value just based on the values that you are covering. So maybe you take the maximum out of them, or you take the average out of them. So it's called a max pooling and average pooling, respectively. So also there's a category called activation functions, which looks like this. So we have a wide range of them, but here I'm just showcasing like 2 of them. So one is the sigmoid function, which is widely used in neural networks, and also the regularized linear unit. So you can easily implement them in official NumPy, but we're just providing some shorthands in the MPX namespace for you so that you don't have to write them on your own. So by plotting them, we can see those. So those are they add nonlinearity to your model so that they can do more things, right? So one last feature I want to talk about is the automatic differentiation functionality. So what it does is actually when you're performing some forward computation on your model, it tracks all the operators that you are using. And also, and then when you want to do a backward propagation, that is calculating the gradient of your model, it backtracks your previous forward computation, and it will help you with all the gradients. And so then in this way, you can avoid defining your own gradient functions that will remind you of your calculus courses back in your college. So this will give you a lot of convenience. So especially when you have a really complex model, that deriving its gradient step by step is a really pain in the back, right? So let's take a look at one example of this. So there's an operation in deep learning called batch normalization. It is performed as this graph shows. So it has in total like 9 to 10 steps. So, and we need the gradient of this from time to time. So let's first take a look at what this guy is doing, right? So we have some input data, And we also have a parameter called gamma, and we also have a parameter called beta, which is the bias. Gamma is like the multiplier. And then for any input data, we are normalizing on the batch dimension of it, right? And then we are calculating, till this point, we're having the variance. And at this point, we're having something like the standard deviation. And then we divide 1 by it. And then we multiply it with the original, like the difference between every data point and the average along the batch dimension. And we want to multiply it with this gamma parameter. And we want to add it with this bias. And then we get the output. So it's in total like 10 steps. So to implement it in official NumPy is like this. So notice one thing is that every operator here, every function I'm using here are from the official NumPy library, okay? And then, so in total there's like 9 steps, right? And in the end, you also want to cache all the intermediate values if you're writing it in official NumPy, because you will need it when you compute the gradient. So let's take a look at how we're doing on it. So we have we randomly generate some data, and we call the function on it. And this just runs smoothly. So as I said, the benefit of having the interoperability is that if you have some helper function that is defined in official NumPy, you can still use it without any problem. So now let's see how we do it in official NumPy. That is, we have we just cast all those tensors to NumPy arrays, and we just call the same function, right? So we get 2 different versions of the output. Now we want to see if we're doing it correctly, right? So we always think the official NumPy is doing perfect, right? So we are now checking against all the data. It's not just about the final output. It's also about we check every intermediate steps. So that we're not just like, say, getting the final answer luckily just by chance, right? So you can see the output of this code snippet is that every output matches for both between our NumPy and official NumPy. So actually, this is not quite painful yet, right? So because we're not doing the gradient thing. So let's revisit this graph and see what do we need to do for the backward propagation. You need to derive the gradient for this guy and this guy, both, right? And then you will have to propagate all those gradients all the way back through the upper branch, which has like 2 sub-branches, right? So this is, and also every single step in this, every single backward step in this could actually remind you of your calculus class, okay? So to do it in official NumPy, let's compare. So it's 9 steps in total that you have to go back, right? So you have to define such a function, and you have to go through all those steps. So still, this is defining official NumPy. So you'll have to get your cached values back, and then you will also have to go through all those steps. And in the end, you are returning the 3 gradients that you are looking for, which is on the input data, on the gamma operator, on the beta operator. So this goes like this, right? So you just randomly initialize some gradient on the output, and then you try to propagate it back, right? So that is how we're testing. And then we can see that this just functions, and it gives out some values for the gradient, for the gamma, for the gradient, the data, and the gamma and the beta, right? So now let's see how do we do it with automatic differentiation. You only have to do like you don't have to write an extra backward function anymore, right? What you do is just like for everything that you want to compute your gradient on, you attach the buffers for holding their gradient values. And then you wrap your forward computation with this record scope so that it can keep track of all the operations you are doing in the forward pass, right? And then See, we don't even need the cache values anymore because we're not computing out of them, right? We just let the underlying library do it. So when you have the buffer ready, when you have wrapped your forward function with your record scope, you can, after the computation, when you want the gradients, you just directly call backward on your output buffer. And then providing it with the gradient, the dout that you want to use. And by this time, every single input's gradient are in their .grad buffers, respectively. So, actually, this will compute all the gradients with respect to the tensor you are calling the backward on. So it will compute for all its variables. So in this case, the DMP out is derived by is obtained through the computation on theta, gamma, and beta. So it's backpropagating to all of them. So let's see, do they match, right? So we're just checking against checking between the grad buffers and the official NumPy's result. So you can see that all of those gradients still match. So we're getting the right answer, but with just way less hassle in the middle with automatic differentiation. So now let's think of how we can build a model that works with this new package. So we're going to operate on this data set, which some of you might know. This is called a fashion MNIST. That is, it contains 28 by 28 images of fashion goods, and we want to categorize them into their corresponding categories, right? So how are we going to do it? Maybe we can build a neural network to do it. So let's prepare our environment first. So we'll be importing the NP and NPX package from MXNet. And here we're calling this function to set the MXNet to its NumPy compatible mode, because we also have some backward compatibility things to address, right? So, and another thing is that we are using the automatic differentiation. So that's why we're importing the autograd, right? The autograd module. And we'll be borrowing the data loader from our Gluon library, but I think we'll be working on getting rid of it. Getting rid of the data loader to make the data loader more NumPy native. So let's first prepare the data loader. You know, when we want to operate on some data, we always want to prepare it first, right? So we set the batch size to be 256. And we are defining some transformations here, which is, you know, you are transferring the image to the individual images to a part of a tensor. And here we are using a parallel data loader. Here the number of workers is set to 4, so that means it will use 4 CPU threads in parallel to load the data, which will accelerate the process. So in the end, we get 2 iterators over the data set. One is for the training set, one is for the test set. So this is not very interesting, but so now let's move on to defining our model. So we want to do a 2-layer multi-layer perceptual model with, so 28 by 28 is just 784 pixels, and we want to categorize them into 10 different categories. And so we designed the network to have 256 hidden nodes. So we initialize all the parameters here, right? We have the weight for the first fully connected layer and the bias for the first fully connected layer. And also the gamma beta, because we are using the batch norm function here. And also we have the second layer's weight and second layer's bias. And to easily manage them, we want to collect them into this collection so that you know, we can access them easier when we are training the model. So for each of the parameters, we definitely want to compute the gradients on them, right? So we're just iterating through this collection and allocate the corresponding memory space for their gradients. So then we move on to define our model, right? So this is, so the first function here is a regularized linear unit function that I talked about previously. We have that available in the NPX namespace too. But here we're just showcasing like we can also do it in the official NumPy. This is just one line code, right? Another thing is that we are defining a simpler version of our batch norm here. So you can see we're not collecting the cached values in the middle. We're just directly returning the output because we're using the automatic differentiation module and we don't need them anymore, right? So here we have the networks. We have the network defined here. So the input is of batch size times 28 by 28. And then we want to reshape them into batch size by 784, which is the shape of our input. And then we dot the input with the first layer's weight, and we add the first layer's bias to it. And then we pass it through the activation function. And then we are also applying a batch norm to the output of the hidden layer. And then finally, we just multiply the normed output with the second layer's weight and add the second layer's bias to it. So in the end, we get a matrix of shape batch size times 10, which is for each of the sample, it gives its output value for each of the 10 categories we want to classify them into. And to keep track of how our model is doing, we're just using the softmax cross entropy loss function. So firstly, softmax is a function that will, for example, for the 10 output categories, it's computing the probability that each of those could be. So the output would sum up to 1 for each sample. And so for each of the sample, what we want to do is that for the ground truth of say it's category 5, right? Then the y value will just be 5, right? And then we want to take the probability from the softmax function and apply a logarithm to it. And we sum the negative values of all of those log values up to get the total loss of the predictions. And also we want to define an optimizer function, which here we're just using stochastic gradient descent with weight decay. So for each of the parameters, when we want to update them, we multiply their gradient with the learning rate and divide it by the total batch size. And we also add this weight decay punishment to it so that we limit the magnitude of all the parameters. So another thing to evaluate our model is that we want to see how accurate it is. That is how much chance, how much probability it has to give the correct prediction, right? Compared to the ground truth of that picture. So to calculate the accuracy, so the y hat value is our predicted value, which is batch size by 10. And the y is just a single label that it may be ranging from 0 to 9. So our model's prediction is just the maximum value out of the 10 categories. So we want to get the index of it. And we compare to the label. And if it's correct, then we just return just 1, right? Otherwise, it's 0. So we sum all those up, and we get the total number of correct predictions. So this is reflected here. And we also want to accumulate on the total number of examples, not just the correct one, also the wrong ones, right? So dividing those two numbers, we get the percentage of giving correct predictions out of our model. So with all those set up, we can now begin training our model. So we are training for like 10 epochs, and the learning rate is 0.5. So for each of the epoch, you can see we are wrapping our forward computation with this record scope. And the network was just defined, right? And then we are also passing it through the loss function. So we want to minimize the loss. So that's why we are computing the gradient of all the inputs and the parameters with respect to the loss function, right? So we're calling the backward function on the loss. So by this point, right? After this function call, the gradient of every single parameter is ready in their corresponding grad buffer, right? So now we can call the optimizer function to optimize our model. And for each of the iteration, we are also keeping track of how we're doing on that batch. So then we are accumulating our loss and our accuracy and also the total number of samples. So for each epoch, after each epoch of training, we also want to evaluate our model on the test data set. That is the data that it has not seen yet, so that we know how well it's gonna be doing when it's put in the wild, right? So we're printing out those values. So if we visualize the whole training loop, it looks like this. So we can see the loss function is actively decreasing, and we are staying at we're increasing the training accuracy and the test accuracy from time to time. And also in the end, we can see they don't differ much. So that means we're good with not having overfitting on the training data set. So if we also want to visualize the predictions of our model, that is, we are actually predicting on actual data. So you can so the upper label is the actual label, the lower label is the predicted label. So we can see for those 4 things, they're pretty obvious. So the model is doing great. So this one might be a bit confusing. So the model is a bit tricked by this. But overall, our model is doing pretty good, I would say. So if we just go back to the slides, after showing all the working samples to you, I would also like to introduce you to, because when we are training model, we're just not doing it for hobby, for fun, right? So we also want to put it into production. So MXNet actually has an easier path for deployment. That is, we actually support in total of 8 language bindings. Except Python, we also have Julia, we have Clojure, we have R, we have C++, we have Perl, we have Java, we have Scala. So it integrates well with all those languages. And especially a lot of them are used in the production systems these days, right? So we also have a big ecosystem. So one thing in the ecosystem is that we have a deep learning textbook that is written based on this new package. And it comes with working code snippets, mathematical formulas, and also we provide a discussion forum if you have any questions. And also if you have any feedbacks. So its Chinese version has already been released last year. It was a #1 bestseller on China's biggest retailer site. And another thing is that it has been adopted by more than 25 universities globally for their deep learning, machine learning courses. So this book is accessible for free at d2l.ai. d2l.ai. And then we also have, in addition to the textbook, we also have several toolkits available for you to use with ready-to-use tools. We have Gluon CV, which is a computer vision toolkit. Gluon NLP is a natural language processing toolkit. Gluon TS is a time series modeling toolkit. And these days, graph neural networks is also on the edge of the trend. So we also have a deep graph library that is deep learning on graphs. So something we want to work on in the future is that we definitely want to extend our operator function coverage. And we also want to further improve our performance of the library. And one way to do it is that we have cooperation with Apache TVM project, which is a deep learning compiler that will generate tunable computation kernels. And also, we want to enable deployment on various hardware, not just big servers. It includes CPU, GPU, and also maybe ARM-based devices. Also via our cooperation with Apache TVM. So that's all for my talk. And also, I provided an IPython notebook containing all the code available at this link. You can actually just find my profile, and it's like the top pinned repo there. Anyone got any questions?
Thank you for the talk. So you showed that this framework can be pretty efficient, pretty fast. What other advantages this framework provides over things like TensorFlow, PyTorch, or other than performance?
Oh, yeah, sure. So firstly, this interface is.
Question, I'm sorry. Can you just repeat the question?
Oh, okay.
Yeah.
So the question is, what does this have? What advantage does this library has over other deep learning frameworks, right? So I think some of them I've mentioned. I think we've got a pretty incorporated, integrated ecosystem. And also, as I said, we have language bindings for you to for easier deployment paths. And also, this very library is fully compatible with NumPy, that you don't have to change any code. That is, you don't have to learn a whole new interface. You know, as we all know, TensorFlow has a very deep learning curve to master, and you know, it's also true for other frameworks that you have to learn new functions. You have to get yourself familiar with all the details of that framework to fully master it, right? So I think that's the advantage of this very package. That is, you don't actually have a lot of learning curve for you, right? You can just directly transition from your NumPy code to this new library.
Yeah, I did. MXNet, that's going to be an Amazon package. It's based in Amazon's product services, right?
No, actually, it's an Apache project, so it's fully open source. It's not hosted within Amazon. Amazon is just one of the key contributors. We also have contributors from the community, and also we have contributors from Intel and NVIDIA who are working on integrating their hardware, their optimized libraries that to accelerate all the workloads, right? So, and also maybe they work on some features, especially for CPU and GPU things. Yeah.
What is the main difference, the reason that it's some sort of 20% faster on some of those base operations than regular NumPy?
Yeah, so I'm going to repeat the question. So what is the reason that it delivers about 20 to 30% just out of package on some of the basic operations? So one thing is that for a lot of the operations, we are integrating with the hardware vendors' libraries, so that may not be adopted by official NumPy. Another thing is that for a lot of the operators, we are providing, we are providing parallel acceleration. We parallelize anything we can parallelize on any operators. But for NumPy, it may not be the case. So I think that is also another reason. Yeah, that's pretty. I think that's pretty much it. Yeah.
So, am I right that the novelty here lies mostly in the fact that the package provides these functions that make writing these algorithms a bit faster, a bit less of a hassle for the programmer?
So again, the question is, so does the novelty lies in the fact that this package provides functionalities that will will allow developers to write the same algorithm with less hassle? Yes. So I mean, accelerating something does not just mean the performance. It's also that we want to cut time on the time for you to write code, to debug your code, to look up the APIs. So I think in this way we are doing the job to firstly let you retain your original functions, interfaces, APIs, and also we are also accelerating during the runtime, right? It's not just the develop time; it's also the runtime, right? So it's both, I would say.
So follow to my question. The question I asked previously was, do you have a comparison of the speed of execution on the GPU versus non-GPU? And you said NumPy doesn't run on GPU, so you need to go through Py or something like that. So the question is, number one, is this framework simplifying? I'm pretty sure you were on the URA talk by running about how that will simplify calling different functions to run on numpy on GPUs. In this case, are you simplifying in those activities? That's number one question.
Mhm.
Yes, no.
Yes.
Okay, so instead of calling CuPy
Mhm.
using numpy, but using MXNet,
Yes.
you can run on GPU.
Yeah, so as one of my examples show, as long as you put your tensors onto GPU, then it just automatically runs on GPU with the same function call, right?
That might be worth noting because
Oh, okay.
if you were on the call on the lecture yesterday, there was this big deal about why a special URA needed to be there because that simplifies your calling instead of going down a different path to run on GPU.
Yeah, I'm gonna go back to that specific example here. That is just a moment. So running this on GPU, right? If you compare it with the code like on CPU, it's just you cast those onto GPUs. You just put them onto GPUs, and all this function call is not changed. So if you have some functions well defined, as I said, in some helper functions, you can just call it as normal, but just put your data on the GPU. So it's always maybe a 2 or 3 lines change depending on how many data you have.
So the fringe benefit, in other words, is you don't have too many changes, but you get the benefit of running on the CPU with the same defined functions you already have.
Yeah, on GPU, you mean, right? Yes.
How is the performance of this compared to NumPy?
That's a good question. We have not. We have not. Oh, sorry. So how does this? So her question was, how does the performance compare to? How does this package's performance compare to NumPy? So my answer is that's a good question. I think we'll be. That NumPy is not a target that we are benchmarking against with. I think we are actively benchmarking against CuPy and JAX, but I don't have the data on hand right now. But if you're interested, I'll reach out to you after we've done the benchmark.
Any specific GPU requirements? Do you need an NVIDIA GPU or will other GPUs also?
So the question was, does this have any specific GPU requirements? So yes, this runs on NVIDIA GPU only, but we actually run with very old versions of those. Even you have SM30 architecture, we would run on it. And also on NVIDIA edge devices such as Jetson TX2, something like that.
Follow up to that. Plans to extend this to other GPUs like Radeon and others?
So the question was, is there any plans to extend the support to other branded GPUs? For that, I think there are 2 paths going forward. One thing is that I think there are some AMD guys in our community talking about adding the support for AMD GPUs. And also, as I said, when through our integration with Apache TVM, we can extend support, operator support to not just AMD GPUs, but also a wide range of devices, such as edge devices, edge GPUs, those kind of things. Any more questions? So we're good? Yeah. Thanks everyone for attending the talk.